Hey, yo, this is actually kinda sick. Turns out my laptop is still better than Journal's Compooper. I'm trying out the mods he's using right now, and hell yeah, they're working like a charm, I'd say. 30 FPS, let's go. I'm still getting a few stutters, but I'm sure that'll disappear soon enough. Once shaders are properly loaded. Right, a boss fight is coming up. I believe some water would be nice here, but... Let me go back to the Korok Forest.
If you're like most people, you've been using base 10 to count things since before you learned what numbers are. Decimal is by far the most common number in system, but in many ways it's clearly not the best way to count things. The number 10 was chosen completely arbitrarily based on the number of fingers most people have, but when you think about it, there are other numbers that would work much nicer as a base. This is decimal, the system that counts by 12s instead of by 10s. All you need is 2 extra digits for 10 and 11, and then you write 12 with 1 0. The standard among mathematicians for writing larger bases is to extend the Arabic numerals using the Latin alphabet, so 10 is written with the letter A, and 11 is written with the letter B. But actually, doing it that way makes 10 and 11 look like they're too separate from the rest of the digits. So you can use an inverted 2 for 10, inverted 3 for 11. But those don't display on most fonts, so you can approximate them with the letters T and E, which also happen to be the first letters of the English words 10 and 11. But actually, as long as we're okay with using the Latin alphabet to represent these digits, then we might as well use X for 10, like in Roman numerals. But actually, now we're back to having them look too different from the other 10 digits, so how about instead we use the Greek letters chi and epsilon? But actually, if we're using Greek letters, then there's no association between the X-looking letter and the number 10, so maybe you can write 10 with the Greek letter delta instead. And all you really need to learn is those 2 new digits, and you're ready to use decimal. First thing that's great about decimal is that it's already common in some contexts, like if you're counting eggs or pastries or inches. Because of this, the vocabulary necessary already exists and doesn't need to be created. You just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, dozen, dozen 1, dozen 2, and so on, until 2 dozen, 3 dozen, 4 dozen, and so on. A dozen is gross, and a dozen gross is a great gross. Okay, so, like, you might run into a problem where when you say 10, people will assume you're talking about the number 12, because that's a problem that happens in real life, I think. So we can call it deck instead, and then we can call 11 L, which is a reference to Stranger Things. Also, I know that earlier I said that we can take advantage of already existing terminology, but let's call 12 dough instead of 12 for a dozen. And then a gross is a row, and a great gross is mo? Yeah, that checks out. Now I know what you're thinking. If we're not taking advantage of existing terminology, what's the point of using decimal at all? Well, there's 2 things that make bases fundamentally distinct from each other. The first is that the more digits a base has, the fewer digits it requires to represent larger numbers. So for example, if you look at every number up to a gross, a bit under a third of them require fewer digits to represent in decimal than they do in decimal. In fact, the larger the numbers get, the more likely it is that the decimal representation will be shorter, and the probability of
What the heck is this?
So for example, if you look at every number up to 1 million, it goes up to 16%. I say goes up, I mean goes down. Okay, that doesn't matter. What does matter is the second each other, which is that the number 12 has way more factors than the number 10. 10 only has 2 prime factors, 2 and 5, whereas 12 has 6 factors, 1, 2, 3, 4, 6, and 12. This makes decimal far more convenient for division. In any base, you can tell what factors any given integer has in common with the base itself just by looking at the final digit. So in decimal, the last digit of any integer is enough information to tell if it's divisible by 2 and if it's divisible by 5, which, as we've established, are the 2 prime factors of 10. In decimal, however, the last digit is enough information to tell if an integer is divisible by any of the 6 factors of 12. Check it out. If an integer ends with 0, it's divisible by 12. If it ends with 0 or 6, it's divisible by 6. If it ends with 0, 4, or 8, it's divisible by 4. If it ends with 0, 3, 6, or 9, it's divisible 3 if it ends with 0, 2, 4, 6, 8, or 10. It's divisible by 2, and hence it's divisible by 1. Divisibility tests are great, but what's even easier to see is how the different bases write simple rational numbers. 1/2 is 0.5 in decimal, because a half is 5/10. 3 doesn't go into 10, so it takes infinitely many digits to represent a third. 4 also doesn't go into 10, so a fourth is 0.25. All of these are very impractical and make decimal unnecessarily hard to use for writing simple ratios. In decimal, all of this is better. A half is 0.6, 6/12. A third is 0.4, 4/12. And a fourth is 0.3, 3/12. As anyone can clearly see, this is objectively simpler than how decimal writes these ratios, and at this point I'm going to break character and ask the question you should be asking right now. Why did I stop at fourths? In decimal, a fifth is one of the simplest fractions to deal with, 0.2, because it's 2/10. However, not only does the number 5 not evenly go into the number 12, it's not even close to going into 12. A fifth is written as 0.2497 recurring. Mathematically speaking, the worst a base can possibly be at writing fifths. If you're the sort of person who wants to be able to quickly divide numbers by 5, decimal suddenly stops looking as good. Decimal? Well, like, decimal. But of course, the number 5 isn't that important, is it? And besides, if you want a base that can easily deal with halves, thirds, fourths, and fifths, you're going to have to use base 60. And regardless, even if decimal is bad with fifths, decimal is bad with thirds, and there's no objective reason to treat thirds as being less important than fifths. Allow me to introduce you to my actual favorite base. I'm Jan Measley, and sextimal is a better base count. 6 is a very nice number. In fact, it's what mathematicians call a perfect number, which has nothing to do with what I'm talking about. As I said before when I was doing jokes, the things that make a base distinct are its size and its factors. We'll go over both of these separately, but before we really get into the why, I'm just going to very quickly go through the how. Okay, numbers up to 12 have the same names as they do in decimal. From there, you count dozen 1, dozen 2, dozen 3, dozen 4, dozen 5, and 13. Multiples of 6 work like multiples of 10, but they end with C instead of T. 6, 12, 30, 40, 50. 6 times 6 is NIF, and NIF times NIF is Unexian. And that's all you need to know to understand this video. Part 1. 6 is a small number. The more digits a base has, the fewer digits it requires to represent larger numbers. The larger a number is, the more the size of the base matters. For any two bases, there is inevitably some number n, where absolutely all numbers larger than n require more digits to represent in the smaller base than they do in the larger base. You can think of this as being the point where the larger base outpaces, or indeed outbases, the other. Now, when you're comparing two bases that are similarly sized, like decimal and decimal, this point is at an extremely large number, 12 to the 13th power in this case. This means that most numbers you deal with will be about the same length in both bases. However, 6 is considerably smaller than 10. The point where decimal outpaces sextimal is at 10,000. A big number, sure, but nowhere near as big as 12 to the 13. Based on this information, you might come to the conclusion that larger bases are inherently better at dealing with larger numbers, and I wouldn't blame you for thinking that. It makes a lot of sense. However, it breaks down when you think about it in the extreme case. Pretend you're Plato and you really like the number 5040, or 3 Unexian 52 Nith, if you were. The point is, you think that it's a great number, and you want to start using it as a base. Since it's a really big base, it's very efficient for writing arbitrarily large numbers. Your Platonic base is able to write 1 million with just 2 digits. Now, in order to actually use such a base, you need to have 2011 gross distinct digits. That's a lot of digits. Clearly, it would be extremely difficult to actually learn how to use it. It's intuitive that one digit in your system contains more information than one digit in decimal. But you don't know that because Arable numerals have... Actually, there's a lot of stuff you're not going to know about, so you should stop pretending to play it. What we need is a way to find a balance between large numbers being too long and individual digits being too numerous. This balance is what's called radix economy, and you can measure how much a number costs in a given base by multiplying
Of course, it's pronounced radix, but what do I know? He's the linguist expert here.
Cost per digit. Long story short, even though the Platonic base can write a million with 2 digits, those digits actually measurably cost more than the 7 digits it takes to write a million in decimal.
Tagma ka? Oh, okay, taka. Where's the Decatree? There he is. That's the last stamina vessel I'll be getting for a while. I'll be focusing on getting to at least 15 hearts should be a good baseline for beating Ganon. Any more would be just overkill and me trying to make the game way too easy, which I don't like. Anyway, I set the resolution to 1080p, but this looks terrible. It looks just as good as the Switch undocked, but I want it to look better. Never. I guess I'll continue playing on not full screen, since it technically looks better that way for me that way.